It's the 5th of December. You can't pull that stool apart because it's chemically bonded. The atoms that make up that stool are held together by really powerful forces. Try pulling your pencil apart. Try pulling your iPad apart. Same thing. The atoms that make them up are held together by chemical forces. Yes, these are notes. Like any of you remember a whole lot about bonding from physical science. You think that's a fair statement? Okay. Even if you remembered everything you did regarding bonding in physical science, we're going to go a little bit deeper in here. Obviously, we should. This is chemistry, not physical science. In physical science, you primarily talk about 2 kinds of bonding. Anybody remember any names? I think somebody said it in the What Do You Know? Somebody said there's ionic. So we're going to talk about 3 kinds, and then we're going to break some of those down into subcategories. But the 3 kinds of bonding we're going to talk about are ionic, covalent, and metallic. Yes, ma'am. Okay, if you don't need to screenshot, I'll go ahead and start talking. Here's the absolutely ridiculous part. I had a year of high school chemistry. I minored in chemistry in college. I had 2 full years of chemistry at the college level. I had been teaching chemistry for 3 years before I finally figured out how to reliably remember ionic versus covalent bonding. That strikes me as dumb, honestly. Now, okay, how many of you already put together that ionic bonds involve ions? There you go. Clever. Good. That's good. I'm glad. Covalent bonds. Who here has been captain, or who here has been on any kind of athletic or team endeavor? Okay. You ever have a team captain? You ever have 2 people who are sharing the responsibilities of captain? What do you call them? Co-captains, because they are sharing the responsibilities of captain. Covalent bonding means that they are sharing. They are co-captains of the valence electron team. Yes, it's stupid that I didn't have a mnemonic for that prior to that. It makes absolutely perfect sense. Somehow I just didn't get it. Those are the 2 big ones that you talk about early on. And we're, like I said, we're going to sort of break that down into more subtle categories because it's not a black and white world like you've been led to believe. The other one that we're going to talk about is metallic bonding. Okay? And that's probably a new one for you. Metallic bonding only happens in transition metals, and actually the book doesn't introduce that till later, but I wanted you to be aware that there are, in fact, 3 types of bonding right off the bat. We'll come back to metallic bonding. So in an ionic bond, you have electrostatic attraction between a positive and a negative ion. They are standing shoulder to shoulder. Stand up. Go ahead, stand up. You can do it. No, really, I mean it. Okay. I would like you with one other person at your table, if possible. Kendra, you can be my buddy. Come here. Stand there, face them. Stand shoulder to shoulder with them. And if you absolutely refuse to play reindeer games, anyway, are any parts of our body actually being shared? No. She's got her body, I got my body. There's no sharing. We're not holding hands. We don't have our fingers interlaced or anything. We're not holding hands. We're just standing shoulder to shoulder. That's an ionic bond. That's all it is. Okay, I'll have you go ahead. Now wait. Not you. You can join with some of them. What if you held hands with that person? Is that too weird for a Tuesday morning? Oh, yes. Can you hold hands? Can you interlace fingers? Will you do it for me? On a Tuesday morning that's rainy and miserable? Some of you will, some of you won't. Okay, that's fine. I get it. You don't have to play along with my stupid reindeer games. If you are interlacing fingers, you're actually sort of sharing your space. That's more like a covalent bond. Something is being held. Okay, you can let go now. I know, that was kind of weird. I apologize. I could have held hands with you. Here, come here, hold hands with me. Come be my covalent bond. So when you have two atoms that are bonded covalently, they're actually sharing. So you've got that sort of interlacing of electron clouds. It's as though they're actually holding hands. In an ionic bond, there's no overlap of their clouds. They're just standing shoulder to shoulder. Now, you tend to get large numbers of positive and negative ions, cations and anions. And so what you get is this very powerful sort of clump of electrostatic attraction between those opposite charges. Okay, now, like I said, we make a habit of simplifying things and lying to you, and then the older you get, the more complicated truths we tell you. So the slightly more complicated truth, because in physical science you just learn that there's ionic and metallic. The truth is that very few things are all ionic or all covalent. I'm sorry, ionic and metallic. Most bonds are partly ionic, partly covalent. Okay? How can that be? Well, imagine you're holding hands, but you're only sort of holding one finger. Or you're just holding pinkies. What determines how covalent or how ionic a bond is basically how much of an electron hog each atom in the pair is. So we went back to that. I'm going to go back to that sort of blanket sharing metaphor. I said, were you ever forced to sleep with a sibling, a cousin, your best friend at a sleepover in 7th grade, and there's one blanket and somebody is a hog. Somebody executes the blanket death roll and takes it. And that's kind of what we're looking at. How strongly each atom attracts electrons. We introduced this concept in the last chapter, electronegativity. How tightly an atom in a bonded pair holds the electrons. Determining bond type is all about electronegativity. That's the foundation of what kind of bond you're going to form. So if we take the most electronegative atom on the periodic table, do you remember what that is? Fluoride, the fluorine ion, and we bond it to the least electronegative atom on the periodic table. We're going to have a difference of 3.3. That is a purely ionic bond. The fluorine will completely take the electrons, the other thing will completely give them up. If we have two identical atoms, hydrogen bonded to hydrogen, oxygen bonded to oxygen, they have identical electronegativities. They're the same thing. They equally want those electrons. They're going to share them evenly, and that's purely covalent. So that's easy. What's a little funkier is the gray area, where it's partly ionic, partly covalent. We talk about ionic character, covalent character. So if you have a difference in electronegativity less than 1.7, it's a covalent bond, but we talk about polar and non-polar covalent. So from a difference of 0.3 to 1.7, that's polar covalent. 0 to 0.3 is non-polar covalent. And we're going to draw a diagram for this because having a bunch of numbers there I don't think really helps. So if we look at it this way, we consider everything in this range ionic. If it's got a difference in electronegativity greater than 1.7, that's ionic. Everything in this space is covalent. But there are some caveats. So we break that covalent up into two parts. We have nonpolar and polar covalent. Have you heard the terms polar and nonpolar before? Where'd you hear them? Just around? Where? In math. Oh! Okay, explain to me how they're used in math, because I can't for the life of me place it. Let me ask you this. Are these elements sharing their electrons well? Are these good sharers? Talk about it at your table. Okay, are the elements in that range sharing? Are they good sharers? Talk at your table. Based on what you know about what we just said. Ionic compounds, big electronegativity difference. One thing really wants the electrons, one thing doesn't. Are they sharing well? What do you guys think, Pacific Northwest? No. Would everybody else agree?
Yeah.
Yeah, these are not sharing well. One steals the electrons completely, one completely gives them up. So when we look at these polar covalent compounds, they're sharing, but do you think they're sharing well? Not especially. One is holding the electrons more closely than the other. So my favorite metaphor for this is a plate of cookies. Who here likes oatmeal raisin cookies? Okay, Madison. Good, and Heaven. So if you guys, and you two seem to be the only people who like oatmeal raisin cookies. I think oatmeal raisin cookies are a waste of good oatmeal. I think raisins are some sort of like moral offense against the entire universe, and they should not be consumed by humans. But you know, I don't have any strong feelings about them or anything. So I'm really glad you two like oatmeal raisin cookies. So if I put a plate of oatmeal raisin cookies in between you, you're likely to share them evenly. If we put a plate of oatmeal raisin cookies between me and you can have them all. So that would be an ionic bond. I am happy to give up the oatmeal raisin cookies. Don't want them. What about peanut butter cookies? Who likes peanut butter cookies? Okay. I like peanut butter cookies. They're good. You know, I could live with, if you told me I could never have another peanut butter cookie in my whole life, I wouldn't cry. I'd be okay with it. I like them. I'll eat them if they're there. So who loves peanut butter cookies? Is there anybody for whom that is their favorite cookie type? Okay, Kobe, Hannah, peanut butter cookies, awesome. So if I put a plate of peanut butter cookies between you and me, you probably like them more than I do. I mean, I like them. I'll eat some. But I'm happy to let you eat the majority of the plate. That is this idea of polar covalent. You're going to get more of the cookies than I am. What about chocolate chip? Who likes chocolate chip? I do. I do. You put a plate of chocolate chip cookies between you and me, I'm going to make sure that for every cookie you get, I get one too. We will be sharing those evenly. I will enforce this, like fork if I have to. You're not going to get more than your fair share, nor am I. That would be a bond where things are shared evenly, the nonpolar. So if we translate this to thinking about the electron cloud, because of course that's what this is coming back to. Okay, if it's ionically bonding, totally exchanging electrons, no sharing required. But if it is polar covalent, and I'll use C and D here, and we're going to go back to drawing that idea of the electron cloud around things. So there's a shared electron cloud, but in a polar covalent bond, what we see is that it's not shared evenly. So we get a larger area of electrons around one of the atoms in the pair. This is the blanket hog. This is you having a slumber party with your cousin who tends to roll up in the blanket, so you're left with a little corner of the blanket. The blanket isn't stripped completely off you, but you're left, you know, largely shivering. That's polar covalent. One is getting a lot more of the electron cloud than the other. Now, in a nonpolar covalent, we'll use, I'm just using letters here because I'm not looking up electronegativities right now. Perfect sharing. Everybody gets the same amount of electron blanket. Everybody gets the same number of cookies. It's even Steven. It's absolutely fair. Okay. Why does this matter? This is another graphic, and you find this one in your book. Basically, we're saying that the more electronegativity difference there is between those two things, the more ionic they are. the less difference in their electronegativity, their desire for electrons, the more covalent they are. And your book, in some points, gets into talking about percentages of ionic and percentages of covalent. We're not going to do that. But I want you to understand this idea that we can characterize them on this continuum. It's not black and white. Okay, now this is important, because this determines how the compounds behave. This determines how these compounds behave. In a nonpolar covalent molecule, there's no overall area of charge. Let's go ahead and I'm going to redraw that. So I had E and E. And the electron cloud is perfectly shared. Any place in that atom, there's likely to be an even distribution of positive and negative charge. So there's no area of the atom that's got more positive than negative or vice versa. But in a polar covalent, that's not the case. So what did I have? C and D.
Excuse me, Mom.
In C and D, where's most of the electron cloud? Around C or D? D. Are electrons positive or negative? Negative. What we end up with is this end of the molecule having a negative charge. It's got a net negative charge. There are more electrons there than protons. It's not really totally neutral. It's not totally charged either. That's why we call it partial charge. And up here on the C end, we've got all these protons without a whole lot of sort of electron blanket. This ends up with a region of partial positive charge. Now, what that means is that these molecules behave in various ways. Water is very polar. A lot of the things we take for granted about water, so tempting, but I won't. A lot of the things we take for granted about the way water behaves, here, I am going to do this. Look at how that beads up. It makes this little bubble of water. That's weird. Look at that. It's not flat. That spill is not flat. It's got elevation. What the heck? It's a liquid, right? Aren't liquids supposed to flow? Look at that. It like beads up. It piles up. Why is that? Why does it do that? That's actually cohesion. Water is adhesive and cohesive. Look at that. They're like little rounded bubbles of water. I'll give you a paper towel later. Did I get everybody's desks wet? Good. Now you can spread them out. You can flatten those little bubbles of water. Why does it do that? Talk about it at your table. Think of a likely explanation related to this. Those water molecules have regions of partial charge, and I'll actually draw the water molecule. Because of those regions of partial charge, we get them sticking together in ways that other things don't. Have you ever drawn water? You know it's Mickey Mouse, right? H, H, O. There's the oxygen. There are the hydrogens. Well, the oxygen, look on your periodic table. Do you have your periodic table out? Get it out. What do you know about periodic trends in electronegativity? So, put your finger on the most electronegative element there is. Need another one? You got your finger on the most electronegative element there is? Fluorine? Good. Electronegativity tends to increase where?
The P block?
Well, as we go across periods, and it tends to decrease as we go down groups. Fluorine, therefore, fits that pattern really nicely with being the most electronegative one there is. I have another periodic table for you because I don't feel like you have enough periodic tables jammed in your notebook. This one doesn't have atomic masses or anything else. It's just got electronegativities. So I'm going to give you this. Okay, so if we look at those electronegativities, what we're going to find is that oxygen is more electronegative than hydrogen. Oxygen being further to the right, it tends to be more electronegative. When we draw the electron cloud around this, and I'm going to draw the electron cloud in some other color, it tends to kind of be like, I don't know, a pair of running pants. It's pretty tight on the hydrogens. There's not a whole lot of wiggle room there. On the oxygen, the electron cloud tends to be more like a comfy, baggy pair of sweatpants. So that electron cloud is pulled pretty tight to hydrogen. So what's basically sticking off the top of the water molecule? Two almost naked protons. So what do we have? Well, we have an area of partial charge here. Mickey's ears are happy. Mickey's chin, not so much. So when we get down to the bottom, to that oxygen molecule, that's got a region of negative charge. Well, that's all well and good, but guess what happens when we put a bunch of water molecules together? They tend to line up because they're attracted to one another. So you have this sort of miniature version of the kind of attraction we see in ionic compounds happening, even though these are polar. I can't get it to line up correctly. There we go. That works. These are polar covalent. So you tend to see forces of attraction within all those water molecules because of those regions of partial charge. The positive ears line up with the negative chins, if we think about it as Mickey. So polar covalent compounds tend to behave differently because of this. And we're going to talk a lot as we go. By the end of this chapter, you're going to be able to tell, you're going to be able to predict how a chemical will behave based on the type of bonding it exhibits. Because everything about how they behave comes down to the kind of bonds that they form. Okay, I am going to put up, well, you know what, let's do a little bit of practice first. So, grab your new periodic table with your electronegativities, and we're going to do some classification. Wasn't recording for that. So we have carbon and hydrogen with a difference of 0.35. So that's going to be a polar covalent bond, just barely polar. Just barely polar, but polar covalent. Okay, let's look at nitrogen and oxygen. Nitrogen and oxygen. Go. So we had nitrogen and oxygen with a difference of 0.4, polar covalent, not by much, but polar covalent. Now let's do sodium and chloride. That makes that an ionic bond. Okay, let's do one more. Let's do magnesium and oxygen. Getting 2.13? Me too. Ionic. What trend do you see here? Look at the location of the elements that are involved in the bonding. Find a trend, talk it over with your table mates. I like the way you express that. Typically when we have things that are relatively close in location, they tend to have similar electronegativities. Remember, electronegativity trends periodically. When we have things on opposite ends of the periodic table from other blocks, we tend to see more ionic character, more ionic bonding. Things that are either strongly polar covalent or that are flat out ionic. When we have things that are side by side, now nitrogen and oxygen are side by side, but oxygen's kind of exceptional, so they do form a polar covalent bond. But typically things that are really close together are going to form more covalent bonds. So when you look at predicting what kind of bond, even if you weren't given a table of electronegativities, you can look at it and say, yeah, side by side, probably covalent. Opposite ends of the periodic table, different blocks altogether. S and P block, probably going to be ionic. The rule that you probably learned in physical science, when I used to teach physical science, this is what I taught. Metals and nonmetals bond covalently. Nonmetals to nonmetal, I'm sorry, metals and nonmetals bond ionically. Geez, Louise Moser. Nonmetals and nonmetals tend to bond covalently. Again, I said we're going to talk about metallic bonding a little bit later, but those are good general trends. Again, in physical science, we simplify things so you get general trend stuff. Here, it's actual numbers. It's hard math. We can determine the actual character of the bond. So I'm going to put up the homework, and I'm going to give you some time to work on it while I work on getting your tests graded, because I think you would like to have those back. I would like to have them back to you. So I'll post the chapter homework, and I'll let you work.